For much of human history, the existence of extraterrestrial life remained a philosophical question rather than a testable scientific hypothesis. Limited observational capabilities and an incomplete understanding of planetary environments reinforced the assumption that life was confined to Earth. Astronomy and biology advanced independently, with little empirical basis for connecting planetary science to the study of life. This perspective shifted as spacecraft exploration of the outer solar system revealed geologically active icy moons. Among them, Europa, orbiting Jupiter at approximately 671,000 kilometers, emerged as a primary focus. Despite its surface temperature and distance from the Sun, geophysical evidence indicates a subsurface ocean beneath its ice shell, maintained by tidal heating rather than solar energy. The presence of liquid water, internal energy sources, and essential chemical constituents positions Europa as a leading candidate for potential habitability, fundamentally reshaping the scientific framework for evaluating life beyond Earth. Europa is not what the solar system was supposed to look like. The solar system that planetary scientists expected to find when spacecraft first began traveling to the outer planets in the 1970s was cold, dead, and simple. The four gas giants, Jupiter, Saturn, Uranus, and Neptune, were understood to be enormous balls of hydrogen and helium with no solid surfaces, and consequently, no interesting geology. Their moons were expected to be frozen, cratered, airless bodies, rocky or icy worlds that had been geologically dead since the early solar system, their surfaces preserved as records of the ancient bombardment that shaped all solid bodies in the solar system's first billion years. The outer solar system was the solar system's deep freeze, a place where temperatures were too low for liquid water, where geological activity had long since ceased, and where the conditions for life were so completely absent that the question did not even arise. The Voyager 1 and Voyager 2 spacecraft, launched in 1977, began dismantling this picture within hours of their closest approaches to Jupiter and its moons. The first dramatic revision came from Io, Jupiter's innermost large moon, which Voyager revealed to be covered in active volcanoes, the most volcanically active body in the solar system, its surface constantly being resurfaced by eruptions that dwarfed anything on Earth. The energy driving Io's volcanism came not from internal radioactive decay, as on Earth, but from tidal heating. The gravitational flexing of Io's interior as its orbit around Jupiter kept it in a state of constant deformation, friction within the moon's rock generating heat at rates sufficient to maintain widespread volcanism. This was a completely unexpected heat source, one that operated independently of a body's distance from the Sun, and that had no precedent in pre-Voyager planetary science. The implications for Europa, Io's neighbour, were immediately recognized by a small group of theorists who had predicted tidal heating before the Voyager encounters. Stanton Peele, Patrick Casson, and Ray Reynolds published a paper in the journal Science in 1979, literally the day before Voyager 1's closest approach to Io, predicting that tidal heating would make Io volcanically active. The same paper noted that Europa, subject to weaker but still significant tidal forces, might also experience significant internal heating, possibly enough to maintain liquid water beneath its icy surface. When Voyager returned the first close-up images of Europa, what the cameras showed was a surface unlike anything in the expected picture of the outer solar system. Europa's surface was smooth, extraordinarily smooth, for a body in the outer solar system that should have accumulated craters from billions of years of bombardment by asteroids and comets. Europa had almost none. The largest impact craters that should have been present on a geologically dead icy moon were simply absent. The surface, at the resolution Voyager's cameras could achieve, appeared to be a vast, relatively flat plain of ice, broken by an intricate network of crisscrossing lines and bands in shades of brown and orange against the white ice background. Some regions showed what looked like broken and refrozen ice, chunks of the ice surface that appeared to have shifted relative to each other and been cemented back together by fresh ice filling the gaps between them, analogous to sea ice on Earth that breaks apart and refreezes. The absence of large craters was the critical observation. Impact craters accumulate on geological timescales, and a surface with few large craters is a surface that has been recently resurfaced, recently enough that subsequent impacts have not yet had time to leave their marks. Europa's near-craterless surface implied geological activity recent enough to erase the impact record, which in turn implied a geologically active body driven by an internal heat source. The most natural explanation, given the tidal heating mechanism already confirmed on Io, was that Europa's tidal heating was sufficient to maintain a subsurface ocean of liquid water, and that this ocean was in contact with the surface through the process of resurfacing that explained the missing craters. The 1979 Voyager encounters provided only tantalizing hints of what Europa might be. The cameras, designed for a flyby at high relative velocity, could not achieve the resolution needed to examine the surface structures in detail. The scientific instruments were not optimized for the specific measurements that would be needed to confirm the presence of a subsurface ocean. The solar system had shown its hand briefly. Europa was clearly not what it was supposed to be, but the cards were not yet fully on the table. That had to wait for Galileo. The Galileo spacecraft arrived at Jupiter in December 1995 and spent 8 years in orbit around the gas giant, making repeated close flybys of all 4 Galilean moons. Its camera system was orders of magnitude more capable than Voyager's, and its science instrument suite was specifically designed to address the questions the Voyager encounters had raised. What Galileo saw when it turned its cameras on Europa confirmed and enormously expanded the Voyager picture. The surface was a world of extraordinary complexity, a global icy shell fractured into a mosaic of plates, bands, ridges, and chaos regions where the ice appeared to have broken down completely and reformed in a jumbled, disordered pattern unlike anything else in the solar system. The chaos regions in particular drew immediate and intense scientific attention. These were areas where the surface ice appeared to have melted or softened enough to allow blocks of older ice to shift, tilt, rotate, and refreeze in new positions. Exactly the kind of surface morphology expected if liquid water or warm, ductile ice existed just below the surface and occasionally breached close enough to the top to disrupt the overlying ice layer. The blocks within chaos regions retained the surface patterns of the surrounding undisturbed terrain, like ice flows on a terrestrial sea, and could sometimes be reassembled by rotating and translating them back to their original positions, confirming that they were displaced fragments of the pre-existing surface rather than independently formed features. Galileo's magnetometer provided the most definitive evidence for a subsurface ocean. Jupiter's powerful magnetic field induces electrical currents in any electrically conducting material it sweeps past as it rotates. A global layer of salty liquid water, salt water being an excellent electrical conductor, would respond to Jupiter's rotating magnetic field by generating its own induced magnetic field. When Galileo flew through Europa's vicinity and measured the magnetic field, it detected exactly this induced field, a magnetic signal varying in sync with Jupiter's rotation, with properties consistent with a global conducting layer at shallow depth beneath Europa's surface. The conducting layer had to be global, covering the entire moon, and had to be at shallow depth within the ice shell rather than at the rock-ice boundary deep in the interior. The most natural and most widely accepted interpretation was a global subsurface ocean of salty liquid water, making Europa the first world beyond Earth confirmed to harbour a large body of liquid water. The solar system had delivered its verdict on the expected picture. The outer solar system was not cold, dead, and simple. One of Jupiter's moons had a liquid water ocean, The implications were staggering, and they took time to fully absorb. The ocean beneath the ice is larger than every ocean on Earth combined. The existence of Europa's subsurface ocean is no longer a hypothesis. It is among the most well-supported conclusions in planetary science, supported by multiple independent lines of evidence, including the magnetometer measurements, the surface geology, the gravity field measurements, the infrared spectroscopy, and theoretical modelling of tidal heating. The ocean is real. What remains uncertain is its specific properties, its depth, its salt content, its temperature profile, its interaction with the seafloor below and the ice above. And these uncertainties are precisely what current and planned missions are designed to constrain. But the existence of the ocean itself is as settled as any conclusion in planetary science. What is known about the ocean scale is remarkable. Europa is a moon roughly the same size as Earth's moon, 3,121 kilometers in diameter, compared to Earth's moon at 3,474 kilometers. Despite this modest size, the ocean beneath its ice shell is estimated to contain between 2 and 3 times as much liquid water as all of Earth's oceans combined. Earth's oceans contain approximately 1.335 billion cubic kilometers of water. Europa's ocean, by current best estimates based on the Moon's interior structure models and the properties of its induced magnetic field, contains somewhere between 3 and 4 billion cubic kilometers. The ocean is global. It encircles the entire Moon, and it occupies the space between the bottom of the ice shell and the top of the rocky seafloor, a layer estimated to be between 60 and 150 kilometers deep. These numbers require some unpacking to appreciate their full significance. The depth of Earth's oceans averages about 3.7 kilometers, with the deepest point, the Mariana Trench, reaching 11 kilometers. Europa's ocean is estimated to be between roughly 60 and 150 kilometers deep throughout its global extent. The pressure at the bottom of Europa's ocean, given the weight of water above and the Moon's surface gravity, would be substantially higher than the pressure at the deepest point of Earth's oceans, but not so extreme as to prevent the kinds of chemical reactions that support life in Earth's deep ocean environments. The temperature throughout much of the ocean volume is uncertain, but is thought to be above the freezing point of salt water. Otherwise, the ocean would not be liquid, and potentially significantly warmer near the rocky seafloor if tidal heating is deposited primarily in the rocky interior, as many models suggest. The ice shell sitting above the ocean is itself a body of scientific interest. Its thickness is one of the most debated parameters in Europa science, with estimates ranging from a few kilometers to several tens of kilometers depending on the thermal model assumed and the interpretation of specific surface features. The debate is not merely academic. The thickness of the ice shell has direct implications for the accessibility of the ocean to surface observations and for any future mission attempting to drill through the ice. Thicker shell models are generally considered more consistent with the overall thermal budget and with the morphology of certain surface features, while thinner shell models are more consistent with some interpretations of the chaos regions and the apparent freshness of some surface materials. Current best estimates from the most comprehensive interior models favour a shell thickness of roughly 15 to 25 kilometres in most regions, though local variations could be significant. The ice shell is not uniform in its properties. It is cold and rigid at the top, where temperatures drop to approximately negative 170 degrees Celsius at the surface. It becomes progressively warmer with depth as tidal heating and the temperature of the underlying ocean raise the temperature toward the melting point. Near the base of the shell, the ice is close to its melting temperature and behaves as a warm, ductile solid rather than the brittle, rigid material at the top, a distinction that has important implications for how the shell deforms, fractures, and exchanges material with the ocean below. The transition between rigid and ductile ice defines a thermal boundary layer that controls the rate of heat transport through the shell and the frequency with which material from depth can reach the surface. The salt content of the ocean is uncertain, but almost certainly non-negligible. The induced magnetic field that Galileo's magnetometer detected requires an electrically conducting ocean, and pure water ice is a poor conductor. The conductivity implied by Galileo's measurements is consistent with an ocean containing dissolved salts at concentrations broadly similar to Earth's oceans, or possibly higher, depending on the specific salt composition. The brown and orange discolorations visible on Europa's surface, concentrated particularly in the fractured and disturbed regions, are attributed by many researchers to salts that have been brought up from the ocean below and deposited on the surface through geological processes, providing a direct chemical connection between the surface material that can be measured remotely and the ocean composition that cannot yet be sampled directly. The specific salts in Europa's ocean are the subject of active debate because different salt compositions would have different implications for the chemistry available to support life. Magnesium sulfate, sodium chloride and sulfuric acid have all been proposed as major dissolved components based on spectroscopic observations of the surface materials. Each composition would reflect different geochemical processes operating at the seafloor and different histories of water-rock interaction since the Moon's formation. The distinction matters for astrobiology. Some salt compositions are more compatible with the chemistry that life on Earth uses than others, though the breadth of environments in which terrestrial life has proven capable of surviving makes any single chemical composition an unlikely absolute barrier. The sheer volume of Europa's ocean, larger than all Earth's oceans combined in a moon smaller than Earth's moon, is itself a statement about the scale of the astrobiological opportunity that Europa represents. Earth's oceans cover 70% of the planet's surface and contain the vast majority of the biosphere's living mass. Life in Earth's oceans ranges from the productive, sunlit surface layers to the perpetually dark deep sea, hydrothermal vent communities that exist entirely independently of solar energy. The total habitable volume of Earth's oceans is enormous, and if even a fraction of Europa's larger ocean is similarly inhabited, the total biomass could be extraordinary. This is speculative, obviously. We do not know whether Europa's ocean contains life at all, but the scale of the oceanic environment is one of the factors that makes Europa's astrobiological potential so compelling. The ice shell is not a barrier. It is a chemical factory. The instinctive reaction to learning that Europa's ocean is buried beneath tens of kilometers of ice is to see the ice as an obstacle, a wall separating the potentially inhabited ocean from the solar system environment, making the ocean inaccessible to observation and cutting off the ocean from the energy sources and chemical inputs that might support life. This reaction is understandable, but wrong. The ice shell is not an inert barrier. It is an active chemical processing system that plays a potentially critical role in making Europa's ocean habitable, and understanding its chemistry is one of the central scientific goals of current and planned missions. The chemistry begins at the surface. Europa's surface is constantly bombarded by energetic charged particles, primarily electrons and sulfur ions. Accelerated to high velocities by Jupiter's powerful magnetosphere and directed toward Europa as the magnetic field sweeps past the Moon in its rotation. These energetic particles carry enough energy to drive chemical reactions in the surface ice that would not otherwise occur at the extreme cold of Europa's surface temperature. The process is called radiolysis, the splitting of molecules by radiation, producing reactive chemical species that can then recombine in new configurations. When water ice is subjected to radiolysis by energetic charged particles, the hydrogen and oxygen atoms in the water molecules are separated, creating a variety of oxygen-bearing compounds, including molecular oxygen, hydrogen peroxide, and ozone. Molecular oxygen and hydrogen peroxide are of particular interest because they are among the most powerful oxidizing chemicals in chemistry. They readily donate oxygen atoms to other molecules, driving oxidation reactions that release energy. On Earth, the presence of molecular oxygen in the atmosphere is the foundation of the high-energy metabolism that powers animals and most complex life. The oxygen produced by photosynthesis dissolved in the ocean or transported there by mixing is what fuels the aerobic metabolism of marine life. If Europa's radiolytically produced oxidants from the surface can be transported into the subsurface ocean, they could provide an analogous energy source for potential life in the ocean even without any sunlight reaching below the ice. The efficiency of radiolytic oxygen production on Europa's surface is estimated to be substantial. Various models, based on the known flux of charged particles from Jupiter's magnetosphere and the measured properties of water-ice radiolysis, suggest that Europa's surface produces oxygen at rates that, when averaged over the ice shell, could be comparable to or exceeding the rates of oxygen supply to Earth's deep oceans, from atmospheric oxygen dissolved at the surface. This is a remarkable statement. A moon in the outer solar system, receiving no photosynthetic input and no direct sunlight on its subsurface ocean, could be producing oxidants at rates comparable to what Earth provides to its deep ocean life through the biological and physical processes of the surface environment. The critical question is whether these surface-produced oxidants are actually delivered to the ocean, or whether they remain trapped in the surface ice indefinitely. The answer depends on the dynamics of the ice shell, specifically on how efficiently material from the cold, radiation-processed surface is cycled downward through the shell toward the ocean. If the ice shell is a static, immobile structure, oxidants produced at the surface will remain near the surface and will not reach the ocean on any timescale relevant to life. If the shell is dynamically active, if there are processes that cycle surface material downward and bring ocean material upward, then oxidants can be delivered to the ocean at rates that might support a significant biosphere. Europa's surface geology strongly suggests that the ice shell is dynamically active. The chaos regions, the ridges, the bands, and the other geological features all point to processes involving the movement of material within the shell and possibly exchange of material between the shell and the underlying ocean. The ridges, by far the most common and most visually striking feature on Europa's surface, are thought to form when tidal flexing of the ice shell opens cracks that expose warmer, softer ice, or even liquid water from depth, which then freezes on exposure to the cold surface and builds up the ridge structure over many tidal cycles. This process inherently involves the transport of material from depth to the surface, and the reverse process, the refreezing of surface material into the shell, would transport surface ice, including any oxidants it contains, downward toward the ocean. The chaos regions provide even more direct evidence for shell-ocean exchange. If the chaos regions form by melting or partial melting of the ice shell from below, then they represent locations where the thermal boundary between the warm, ductile lower shell and the cold, rigid upper shell has moved close to the surface, locations where the vertical distance between surface and ocean is minimized and where chemical exchange is most likely to occur. The brown discolorations in chaos regions, attributed to upwelled ocean material, provide direct observational evidence for the upward transport of ocean chemistry to the surface in these locations. The downward transport of surface oxidants in the same regions is a natural companion process. The sulfur chemistry adds another layer of complexity. Jupiter's volcanic moon Io continuously ejects enormous quantities of sulfur dioxide and sulfur particles into the Jovian magnetosphere, where they are ionized and accelerated. Some of this sulfur is deposited on Europa's surface, where it contributes to the radiation chemistry and produces sulfuric acid as a major component of the surface chemistry. Sulfur is a critical element for life on Earth, where sulfur-reducing and sulfur-oxidizing bacteria represent major branches of the metabolic tree of life, particularly in deep-sea hydrothermal environments. If Io-derived sulfur is being delivered to Europa's surface and then cycled into the ocean through shell dynamics, it would be providing a biologically important element to the ocean from an entirely external source, a geochemical link connecting Io's volcanism to Europa's habitability through the Jovian magnetosphere. The chemical factory of Europa's ice shell therefore operates as a multi-stage processing system. Energetic charged particles from Jupiter's magnetosphere drive radiolysis of surface water ice, producing molecular oxygen and hydrogen peroxide. Sulfur from Io's volcanism is deposited on the surface and contributes to the radiation chemistry. The dynamically active ice shell cycles these surface processed materials downward toward the ocean at rates that depend on the specific mechanisms of shell dynamics and their timescales. The ocean receives these materials as chemical inputs that, combined with the chemistry of the rocky seafloor below, create a potentially rich chemical environment. The ice shell is not an obstacle to habitable ocean chemistry. It is an essential component of the system that might make the ocean habitable. The seafloor may be doing exactly what Earth's seafloor did 4 billion years ago. The discussion of Europa's habitability almost always begins with the liquid water ocean, and rightly so. Liquid water is the universal solvent of biochemistry and the first requirement for any environment that might support life as we understand it. But liquid water alone is not sufficient for life. Life requires energy, a source of chemical potential that can drive the metabolic reactions that build biological molecules, reproduce cells, and maintain the organized complexity that distinguishes living systems from their environment. It requires the right chemical building blocks, the carbon, nitrogen, phosphorus, sulfur, and trace elements that form the molecular machinery of cells. And it requires some mechanism for concentrating and organizing these ingredients in ways that allow complex chemistry to proceed. On Earth, the seafloor provides all three of these requirements in one of the most consequential geological structures ever studied, the hydrothermal vent. Hydrothermal vents form where seawater percolates into fractures in the seafloor, is heated by the hot rock and magma below, reacts chemically with the minerals it encounters, and returns to the ocean floor enriched with dissolved minerals and heated to temperatures that can exceed 400 degrees Celsius. The hot, mineral-laden fluid that erupts from hydrothermal vents is chemically distinct from the surrounding seawater, creating steep chemical gradients at the vent-seawater interface. These gradients carry free energy, chemical potential that can be harvested by living organisms as the vent fluid and seawater mix and react. The communities of life that live around Earth's hydrothermal vents, discovered in 1977 during the same era that the Voyager spacecraft were revealing the outer solar system, are among the most significant biological discoveries of the 20th century precisely because they demonstrated that life does not require sunlight. The organisms living around deep-sea hydrothermal vents, tube worms, clams, shrimp, and the chemosynthetic bacteria that form the base of the food chain, obtain their energy entirely from the chemical reactions driven by the mixing of vent fluid and seawater. The energy source is geochemical rather than solar, the oxidation of hydrogen sulfide and other reduced compounds that emerge from the vents by the oxygen dissolved in the seawater. The vent communities are islands of biological productivity in the otherwise near-barren deep ocean, driven entirely by geological energy independent of any photosynthetic contribution. A specific type of hydrothermal vent, called the alkaline hydrothermal vent, represented on Earth by structures like the Lost City vent field in the Atlantic Ocean, has attracted particular attention from astrobiologists studying Europa because its chemical character may be especially relevant to life's origins and to the potential habitability of ocean worlds. Alkaline hydrothermal vents form not from magmatic heat, but from a chemical reaction called serpentinization. The reaction of seawater with olivine and other iron and magnesium silicate minerals in the oceanic crust, which produces heat as a byproduct and generates hydrogen gas and highly alkaline fluid. The hydrogen gas is a powerful reductant that can serve as a primary electron donor for metabolism, while the alkaline fluid creates proton gradients at the vent-seawater interface, analogous to the proton gradients that power ATP synthesis in all living cells. Some researchers, most prominently the geochemist Michael Russell and his collaborators, have proposed that alkaline hydrothermal vents were the setting in which life on Earth originated, that the combination of hydrogen-rich fluid, mineral-lined pore structures that could concentrate organic molecules, proton gradients that could drive proto-metabolic reactions, and the chemical energy available from hydrogen oxidation provided the exact conditions needed to bootstrap the first self-replicating chemical systems. Whether or not this specific hypothesis is correct, and it remains debated, the broader point is that alkaline hydrothermal vents provide a self-sustaining chemical energy source that does not depend on any external input, driven entirely by the geochemical reaction of water with rock. Europa's seafloor almost certainly supports water-rock interaction. The rocky interior, composed primarily of silicate minerals similar in composition to Earth's mantle, is in contact with the liquid ocean above. Tidal heating deposits energy throughout the interior, maintaining warm conditions that drive the same serpentinization reactions that produce alkaline hydrothermal vents on Earth. Theoretical models of Europa's interior suggest that the rate of water-rock interaction at the seafloor is substantial, and that hydrogen production through serpentinization is likely an ongoing process. The hydrogen produced would dissolve in the ocean water and be available as a potential energy source for any chemosynthetic organisms that might inhabit the ocean floor. The geochemical analogy to the early Earth extends further. 4 billion years ago, Earth's ocean floor was actively being produced at mid-ocean spreading centers and consumed at subduction zones, much as it is today. But the chemistry of the ocean itself was very different from today's oxygenated ocean. The early Earth's ocean was reducing rather than oxidizing. It contained dissolved iron and other reduced metals rather than the dissolved oxygen that characterizes the modern ocean. And life that emerged in this environment necessarily had to work with the available chemistry rather than the oxygen-rich chemistry that modern aerobic life exploits. The hydrothermal vent communities of the early Earth were chemosynthetic, deriving energy from the geochemical gradients of the reducing vent environment rather than from photosynthetically produced oxygen. Europa's ocean environment has many parallels to the early Earth ocean. The absence of photosynthesis means the ocean is not producing biological oxygen, and without oxidant input from the surface through ice shell cycling, the ocean would be a reducing environment similar to the early Earth's. The delivery of surface-produced oxidants through shell dynamics introduces a complicating factor, potentially providing an electron acceptor that could enable aerobic-like metabolism. But the baseline condition of the deep ocean, far from any surface influence, may resemble the chemosynthetic, geochemically fueled environment of Earth's early hydrothermal vent communities. This parallel is not merely metaphorical. If life originated on Earth in conditions similar to what currently exists at Europa's seafloor, then Europa's seafloor is not just a hypothetically habitable environment. It is an environment analogous to the specific setting where life is believed to have begun on at least one world we know of. The scientific significance of this parallel is difficult to overstate. It transforms Europa from an environment that might support life to an environment that represents a natural experiment. Has the origin of life process, apparently possible in Earth's early hydrothermal vent conditions, occurred independently on a similar world in a different part of the solar system? The discovery that broke the rules about where life can exist. The concept of the habitable zone, the range of distances from a star at which a planet's surface temperature would allow liquid water to exist, was one of the organizing frameworks of astrobiology for the second half of the 20th century. In its original formulation, the habitable zone was defined entirely by the stellar energy flux. Too close to the star, and a planet's water boils. Too far, and it freezes. The habitable zone around the Sun extends roughly from the orbit of Venus to slightly beyond the orbit of Mars, with Earth sitting comfortably in the middle. This framework was tremendously useful for prioritizing targets in the search for life, both within the solar system and in the growing catalogue of extrasolar planets. Europa violated this framework completely. It orbits Jupiter at 5.2 astronomical units from the Sun, well beyond Mars, far outside the Sun's habitable zone by any conventional definition. The surface temperature of Europa is approximately negative 170 degrees Celsius, colder than any environment on Earth and colder than any environment in which terrestrial life has ever been found surviving, rather than just persisting in a dormant state. By the traditional habitable zone criterion, Europa should be definitively uninhabitable, frozen, dead, irrelevant to the search for life. Yet Europa has a liquid water ocean. The energy that maintains that ocean is not solar energy. It is tidal energy, generated by the gravitational flexing of Europa's interior as it orbits Jupiter in a slightly elliptical orbit that keeps it in constant tidal interaction with both Jupiter and with the other large Galilean moons. The tidal dissipation converts orbital and rotational kinetic energy into heat within Europa's interior at a rate sufficient to maintain a global liquid ocean, despite the extreme cold of the outer solar system. This heat source is completely independent of stellar radiation and has no analogue in the traditional habitable zone concept. The discovery that tidal heating could maintain a liquid water ocean in the outer solar system required the habitable zone concept to be fundamentally revised. The traditional concept was too narrow. It accounted for only one energy source relevant to planetary habitability, when the solar system itself was demonstrating that at least one other energy source existed and operated on a scale sufficient to maintain one of the largest bodies of liquid water in the solar system. The revised concept, now widely used in astrobiology, is the concept of the continuously habitable zone for stellar radiation purposes, alongside recognition that internal energy sources, tidal heating, radioactive decay, residual accretion heat, can maintain liquid water at any distance from a star if the specific conditions of a planetary body's internal structure and orbital configuration provide sufficient internal energy. This conceptual revision had immediate and profound consequences for estimates of the prevalence of potentially habitable environments in the universe. If habitable environments can exist at any distance from a star, provided the body has an appropriate internal energy source, then the fraction of potentially habitable bodies in the universe is not constrained by the fraction of planets in stellar habitable zones. Every icy moon in the solar system with sufficient tidal heating is a potential ocean world. Every icy planet in the outer reaches of a stellar system, if sufficiently massive to retain internal radioactive heating, is a potential ocean world. The universe's population of potentially habitable environments expanded by orders of magnitude the moment Europa's ocean was confirmed. The parallel expansion affected the scientific framework for thinking about life itself. The discovery of hydrothermal vent communities on Earth in 1977 had already demonstrated that life could exist without sunlight, provided geochemical energy was available. The confirmation of Europa's ocean extended this lesson to an entire world, not just isolated communities at isolated vents, but potentially a global ocean at a world where the primary energy source is geochemical rather than solar. The combination of these two discoveries, life without sunlight on Earth, a liquid ocean without sunlight at Europa, established the principle that liquid water plus geochemical energy is a sufficient combination for habitability regardless of solar energy, and that this combination exists at least once in the outer solar system and may exist throughout the universe wherever icy moons orbit massive planets with appropriate tidal interactions. The implications went further still when the parallel with extremophile research on Earth was fully appreciated. Beginning in the 1980s and accelerating through the 1990s and 2000s, microbiologists discovered life in environments on Earth that had previously been considered definitively uninhabitable. Life in boiling hydrothermal fluids, life in highly acidic mine drainage, life in hypersaline lakes, life in the permanently frozen sediments of Antarctic permafrost, life in the crushing pressures of the deepest ocean, life in the radiation-intense environment of nuclear reactor cooling ponds. Each discovery pushed the boundaries of what was considered possible, until the emerging scientific consensus recognized that wherever liquid water exists on Earth, in any form, at any temperature between the freezing and boiling points of water at the relevant pressure in virtually any chemical environment, some form of microbial life manages to survive. The convergence of these discoveries pointed toward a radical simplification of the habitability criterion. Liquid water is both necessary and sufficient for life, at least at the microbial level, provided the basic chemical building blocks are present. Whether Europa meets this simplified criterion depends on whether its ocean contains the necessary chemical building blocks alongside its liquid water. Current understanding of Europa's chemistry, the water-rock interaction at the seafloor, the delivery of organic rich material by cometary and asteroid bombardment throughout the solar system's history, the synthesis of complex chemistry in the radiation-processed surface ice suggests that the chemical building blocks are likely present. The ocean is the right solvent. The chemistry is probably right. The energy is available. By every criterion that scientific understanding can currently apply, Europa's ocean is habitable. Habitable does not mean inhabited. The gap between an environment that could support life and an environment that actually contains life is the gap between the conditions for origin and the event of origin itself. A distinction that may be bridgeable by natural processes given sufficient time, or may require specific conditions beyond mere habitability that Europa does or does not possess. But the demonstration that Europa meets the habitability criteria represents a dramatic expansion of the universe's life-supporting potential, and it is the foundation on which every scientific and programmatic argument for sending spacecraft to Europa is built. Europa's surface is one of the most geologically active places in the solar system. The surface of Europa is young. Not young in the sense that planetary geologists use for old, but recently resurfaced terrains, and not young by the standards of a geologically active inner planet like Earth. Young in the absolute sense. The average age of Europa's surface is estimated from crater counting statistics and theoretical models of impact rates in the outer solar system to be between 40 and 90 million years. In a solar system that is 4.5 billion years old, a surface with a mean age of 60 million years is extraordinarily recent. The equivalent, if Earth's surface were proportionally aged, of a surface that formed during the Cretaceous period when non-avian dinosaurs were still alive. A young surface means a constantly resurfaced surface. The craters that should have accumulated over billions of years of bombardment are not there because the geological processes that created the current surface erased them, continuously renewing the ice to produce the near craterless terrain that first attracted attention in the Voyager images. The processes responsible for this continuous resurfacing are among the most scientifically interesting features of Europa, because they are the same processes that exchange material between the ocean and the surface. The processes that deliver ocean chemistry to the surface, where it can be observed, and that may deliver surface-produced oxidants to the ocean, where they could support life. The ridges are the most abundant geological feature on Europa's surface, covering a significant fraction of the total surface area and appearing virtually everywhere that high-resolution imaging has been achieved. They come in a variety of forms: simple, single ridges a few hundred meters wide and a few tens of meters high. Complex ridges with multiple parallel crests and troughs. Ridge bands that are tens of kilometers wide and show evidence for spreading, the lateral separation of the surface on either side of the band, opening a gap that is filled with fresh material from below. The formation mechanism for ridges involves the tidal flexing of Europa's ice shell, opening cracks on each tidal cycle, pumping a small amount of warm ice or liquid water from depth into the crack, and building the ridge incrementally over thousands of tidal cycles as the material freezes and accumulates at the surface. The chaotic terrain, the chaos regions, represents the most extreme form of surface disruption on Europa. These regions, which cover roughly a quarter of Europa's total surface, show evidence for the wholesale disruption of the pre-existing ice shell, with blocks of older surface material floating in what was evidently a mobile, liquid or mushy matrix before everything refroze. The two competing formation models for chaos regions differ in their implications for the ocean depth and the mechanism of heat delivery. The thin shell model proposes that chaos regions form when the ocean melts through to within a few kilometers of the surface, flooding the underside of the rigid upper ice shell and causing it to break up and float on the liquid before refreezing. The thick shell model proposes that chaos regions form through the partial melting of the lower, ductile portions of the shell by warm diapirs, blobs of warm, buoyant ice rising from the shell-ocean boundary, without the ocean actually breaching to near-surface depths. Both models agree that chaos regions represent locations where the thermal and chemical connection between ocean and surface is maximized. The thin shell model implies direct contact between ocean water and surface ice in the chaos-forming episodes, while the thick shell model implies efficient transport of ocean-derived chemistry by the rising diapirs. Either way, the brown discolorations that are preferentially concentrated in chaos regions, the same discolorations attributed to salts and other non-ice materials brought up from depth, provide direct observational evidence for the upward transport of ocean-derived material to the surface in these regions. The lenticular, small circular features ranging from a few kilometers to roughly 10 kilometers in diameter are scattered across Europa's surface in a distribution that has attracted significant scientific attention because they may represent the surface expression of rising warm ice diapirs, similar to salt domes on Earth where buoyant salt bodies rise through denser rock and create dome structures at the surface. If lenticulae are diapir heads, they identify specific locations in the ice shell where the ocean ice boundary is being actively disturbed and where chemical exchange between ocean and surface is currently occurring. The spatial distribution of lenticulae would then be a map of current geological activity, marking the places most likely to have fresh ocean-derived material at or near the surface. The pits, spots and domes that accompany the lenticulae in some regions add further complexity to the picture of subsurface activity. Pits may form where warm material has risen and then drained back, leaving a surface depression. Domes may be the direct surface expression of diapirs that have pushed the overlying rigid ice upward without breaking through. The variety of surface expressions associated with what appears to be a common underlying process, the rise of warm, buoyant ice from the lower shell, suggests a range of different timescales, depths, and intensities of subsurface activity, producing recognizably different surface signatures. One of the most intriguing recent developments in Europa's surface science, prior to the launch of current missions, was the identification of potentially young or currently active regions based on the freshness of specific surface features. Some ridge systems show evidence of very recent activity. Their surfaces are essentially craterless, even relative to the already young global average, implying formation within the last few million years or less. Some chaos regions show internal structure suggesting multiple episodes of disruption and refreezing over relatively short timescales. If any surface regions are currently active, if tidal cycling is right now opening cracks, pumping material, and resurfacing small areas of Europa's ice, then those regions represent the locations most directly sampling the current state of the ocean beneath. The geological activity of Europa's surface is not merely scientifically interesting as an end in itself. It is the physical mechanism that connects the ocean to the surface, that creates the chemical transport pathways between the deep habitable environment and the accessible surface where remote observation and eventual sample collection are possible. Understanding the geological processes in detail, their rates, their locations, their depths of origin, is the key to understanding how to use Europa's surface as a window into the ocean beneath. This is why the mapping and characterization of Europa's geological activity is a primary objective of both the Europa Clipper and the ESA JUICE missions currently operating or en route to the Jovian system. The plumes changed everything about what a mission to Europa could actually achieve. In 2012, astronomers using the Hubble Space Telescope detected what appeared to be water vapor plumes erupting from Europa's south polar region. The detection, made in ultraviolet light by observing the silhouetting of the plumes against Jupiter's disk as Europa passed in front of the planet, showed water vapor reaching heights of approximately 200 kilometers above Europa's surface before falling back or dispersing into space. A subsequent detection in 2016 showed similar features in a similar location, adding confidence that the initial observation was not instrumental noise. In 2017, researchers reanalyzing data from Galileo's close flybys of the 1990s found magnetic field perturbations consistent with Galileo having flown through an active plume during one of its Europa passes, a detection hiding in old data that was only recognized once the Hubble observation suggested where to look. The analogy to Enceladus was immediate and inescapable. Saturn's moon Enceladus had been found by the Cassini spacecraft to be venting plumes of water ice and vapor from its south polar region, with the plume material sampling the moon's subsurface ocean directly. Cassini had flown through Enceladus's plumes and measured their chemical composition, detecting not just water vapor and ice, but complex organic molecules, silica particles consistent with high-temperature water-rock interaction, and molecular hydrogen, direct evidence for active hydrothermal processes in Enceladus's ocean. These measurements had transformed Enceladus from an interesting geological curiosity into one of the highest priority targets in astrobiology, precisely because the plumes made it possible to sample the ocean without drilling through the ice shell. If Europa's plumes were real and persistent, they would offer the same extraordinary scientific opportunity. A spacecraft flying through an active plume would be directly sampling material from Europa's ocean, measuring its chemical composition, searching for organic molecules, detecting potential biosignatures, without needing to land, drill, or otherwise interact with the ice surface in the mechanically demanding and technically challenging ways that any direct ocean access would otherwise require. The plumes would be, in effect, an ocean sample delivery service operating on Europa's behalf, continuously ejecting ocean material into space, where a passing spacecraft could analyze it. The scientific potential of plume sampling is almost incomprehensibly large relative to what remote sensing from orbit can achieve. Remote observation of Europa's surface can measure the composition of surface materials, map the geological structures, and constrain the bulk properties of the ice shell, but it cannot directly measure what is in the ocean. A spacecraft flying through a plume and measuring the composition of the plume material would be directly measuring ocean chemistry, the salts dissolved in the ocean water, the organic molecules present, the redox chemistry reflecting the metabolic environment, and potentially even cellular material if life exists in the ocean and is being swept up into the plumes along with the water. The uncertainty about Europa's plumes has not diminished the mission planning implications of their potential existence. Both the Europa Clipper mission and the science community that shaped its design incorporated the possibility of plume encounters as a high-priority science opportunity, ensuring that the spacecraft's instruments were capable of analysing plume material if any plumes were encountered during the mission's many Europa flybys. The decision to design for plume science without certainty that plumes existed was a reasonable scientific bet. The evidence was suggestive enough that failing to design for plume encounters would be a significant missed opportunity if the plumes proved to be real, while the cost of including plume science capability was modest, given that the instruments needed for plume analysis are a subset of those needed for the broader science objectives anyway. The plume detections, tentative as they are, change the psychological and strategic framing of Europa exploration more broadly. Before the plume hints, the path from orbital observation to ocean science seemed long and technically daunting, requiring a lander, years of operations on the surface, and ultimately a drilling capability beyond any previously deployed in the solar system. The plumes suggested a shortcut. If the ocean was ejecting material into space, a spacecraft with the right instruments in the right place at the right time might learn as much about Europa's ocean chemistry from a flyby as a drilling mission would learn from direct access. This possibility shifted the perceived scientific return of the Europa Clipper mission from primarily surface characterization, interesting but not directly answering the question of habitability, to potentially direct ocean sampling, which could answer the habitability question definitively and might even detect biosignatures if life is present. The parallel with Enceladus is instructive here, but not perfectly applicable. Enceladus's plumes are persistent, geologically controlled features associated with specific surface fractures called tiger stripes that have been continuously active since Cassini first observed them. Europa's putative plumes, by contrast, appear intermittently and have not been definitively confirmed to the same standard as Enceladus's. The intermittent character could reflect geological variability, plumes forming when tidal stresses open specific fractures and ceasing when those fractures close, which would make predicting when and where to intercept a plume a significant operational challenge. It could also reflect limitations in the detection technique. The Hubble detections are at the edge of the instrument's sensitivity, and the apparent intermittency might partly reflect variable observing conditions rather than genuine temporal variability in the plume activity. The Europa Clipper's close flybys of Europa will provide far more sensitive plume detection capability than Hubble can achieve from Earth orbit, and the magnetic field and plasma measurements will be able to detect the disturbance caused by even a modest plume. Whether the mission encounters active plumes and what they reveal about the ocean beneath them is one of the most consequential open questions in current planetary science. NASA's Europa Clipper is the most capable planetary science mission ever launched. On October 14, 2024, a SpaceX Falcon Heavy rocket lifted off from Kennedy Space Center carrying a spacecraft the size of a basketball court, the largest planetary science spacecraft NASA has ever built, on a trajectory that will take it on a 5.5-year journey to Jupiter. The spacecraft is the Europa Clipper, and its launch represented the culmination of more than 2 decades of scientific advocacy, engineering development, and funding battles that at several points came close to killing the mission entirely before it reached the launch pad. It is the most capable planetary science instrument ever sent beyond Earth orbit, carrying a suite of 9 science instruments designed to characterize Europa's ocean, ice shell, surface chemistry, and geological activity in sufficient detail to make a comprehensive assessment of the Moon's habitability and to identify the most promising targets for any future landing mission. The Europa Clipper's mission architecture is ingenious, given the constraints of the Jovian radiation environment. Placing a spacecraft in orbit around Europa itself, the most direct approach to studying the Moon continuously, was rejected because Jupiter's radiation belts at Europa's orbital distance are so intense that even the most heavily shielded spacecraft would suffer fatal electronics damage within a few months. Instead, the Europa Clipper will orbit Jupiter itself in a large elliptical orbit that takes it far from the radiation belts between Europa encounters, but brings it close to Europa for a series of 49 planned flybys over 4 years of operations. During each flyby, which will take the spacecraft within 25 kilometers of Europa's surface at closest approach, the spacecraft will collect data with all 9 instruments before retreating to the radiation cooler portions of its orbit to transmit the data back to Earth and prepare for the next flyby. This flyby architecture accumulates coverage of Europa's surface and space environment in a way that eventually rivals orbital coverage, while limiting the total radiation dose to levels that the spacecraft's hardened electronics can survive. The 49 planned flybys will sample different latitudes, longitudes, and local times on Europa's surface, building up a comprehensive picture of the Moon's global properties while providing detailed characterization of specific high-interest targets in the close approach portions of each flyby track. The Science Instrument Suite is designed around the core questions of Europa habitability. Does the ocean exist, and what are its properties? Is the ice shell active, and what are the exchange processes with the ocean? What is the composition of the surface materials, and what does it tell us about the ocean chemistry? Are there plumes, and what is their composition? The instruments address these questions through complementary approaches that reinforce and cross-check each other. REASON, the radar for Europa assessment and sounding of ocean to near surface, is the instrument perhaps most directly aimed at the ocean itself. It is an ice-penetrating radar that will transmit radio waves downward through Europa's ice shell and detect the reflections from internal interfaces, including the potential ocean surface at the base of the shell. The radar has the capability to penetrate ice up to roughly 30 kilometers thick, covering the full range of ice shell thickness estimates. If it detects a strong reflection from the base of the ice shell, it will confirm the ocean's existence independently of the magnetic measurements, and it will constrain the shell thickness directly, one of the most debated parameters in Europa science. The MASSPEX mass spectrometer is designed to detect and characterize organic molecules in any plume material the spacecraft encounters. It is an extraordinarily sensitive instrument capable of detecting molecules at concentrations many orders of magnitude below what previous mass spectrometers could measure, specifically optimized for the detection of complex organic chemistry that might indicate biotic or prebiotic processes. If the spacecraft flies through an active plume with significant organic content, MASSPEX will provide the most detailed organic chemistry profile of any extraterrestrial ocean material ever measured. The magnetometer and plasma wave instruments will characterize the magnetic environment of Europa and refine the induced magnetic field measurements that provided the primary evidence for the ocean's existence from Galileo. The improved measurements from many repeated flybys will constrain the ocean's electrical conductivity, and therefore its salt content, far more precisely than Galileo's limited flybys allowed, and will search for evidence of localized variations in the ice shell that might indicate thin spots or active geological regions. The ultraviolet spectrograph will search for plumes directly, using the same technique that produced the Hubble detections, but from a far closer vantage point with far greater sensitivity. Surface and atmospheric composition measurements from the infrared spectrograph will constrain the chemical nature of the non-ice surface materials, the salts, the organic compounds, the radiation products that carry information about the ocean chemistry and the processes connecting ocean to surface. The mission's cost, approximately $5 billion, including development, launch and operations, reflects the ambition and capability of the science objectives and the engineering demands of the Jovian radiation environment. It is one of the most expensive planetary science missions in NASA history, and its funding journey was rocky enough that the mission's eventual approval and completion represent as much an achievement of scientific advocacy as of engineering. The case for Europa's scientific importance had to be made repeatedly against competing priorities and budget pressures over 2 decades, a story worth examining in its own right, which appears later in this narrative. The ESA JUICE mission and why 2 spacecraft are better than 1. While NASA's Europa Clipper represents the most direct and comprehensive assault on the question of Europa's habitability, it is not the only spacecraft currently en route to investigate the Jovian moon system. The European Space Agency launched its Jupiter Icy Moons Explorer, JUICE, in April 2023, beginning an 8-year journey to Jupiter that will arrive in 2031. JUICE is Europe's largest and most complex planetary science mission, and while its primary destination is Ganymede, the largest moon in the solar system, and itself a world with a confirmed subsurface ocean, it includes 2 Europa flybys in its science program that will provide data complementary to the Clipper's comprehensive coverage. The JUICE mission's focus on Ganymede rather than Europa reflects a deliberate scientific strategy of characterizing the full family of Galilean moons rather than concentrating all resources on Europa alone. Ganymede, Callisto, and Europa all appear to harbour subsurface oceans, making the Jovian system a unique laboratory for comparative ocean world science. Each moon occupies a different position in Jupiter's tidal heating gradient. Io receives the most intense tidal heating, Europa moderate heating, Ganymede less, and Callisto essentially none, and each has a different internal structure, different ice shell properties, and different surface geology reflecting these differences in heating and composition. Understanding how these differences produce different ocean properties and different degrees of habitability requires studying all the ocean worlds, not just the most promising one. JUICE carries 10 science instruments that will make comprehensive measurements of Ganymede's magnetic field, ice shell, subsurface ocean, surface composition, and space environment, as well as measurements of the broader Jovian system during the spacecraft's approach and cruise phases. When it enters orbit around Ganymede in 2034, becoming the first spacecraft ever to orbit a moon other than Earth's, it will conduct a systematic characterization of Ganymede's properties comparable in ambition to what the Clipper will achieve for Europa. The 2 Europa flybys in JUICE's science program, while modest compared to the Clipper's 49, will provide measurements in wavelength ranges and with instrument types that complement rather than duplicate the Clipper's observations. JUICE's ultraviolet spectrograph operates at slightly different wavelengths than the Clipper's and will provide independent measurements of Europa's exosphere and any plume activity. JUICE's radar sounder uses different frequencies than REASON and will therefore probe different depth ranges in the ice shell, providing information about ice shell structure at scales complementary to the Clipper's radar. The combination of the 2 spacecraft's measurements will be more powerful than either alone for constraining the ice shell's internal structure. The coordination between the Europa Clipper and JUICE missions represents a broader trend in planetary science toward multi-mission, multi-agency approaches to high-priority targets. The science questions at Europa are complex enough, and the potential significance of the answers large enough, that a single mission, even one as capable as the Clipper, cannot address all aspects of the problem with the thoroughness that the scientific community considers necessary. The 2-mission approach distributes the scientific risk. If either spacecraft suffers a significant technical problem, the other can still address the most critical scientific questions. It also distributes the scientific workload. Different instruments, different flyby geometries, and different temporal coverage build up a more complete picture of Europa's properties than any single mission could achieve. The difference in arrival times, the Clipper arriving at Jupiter in April 2030, JUICE arriving in 2031, means that both spacecraft will be operating simultaneously in the Jovian system for an extended period, enabling coordinated observations that are impossible when a single spacecraft operates in isolation. Simultaneous measurements from two different positions in the Jovian system can constrain the dynamic properties of Jupiter's magnetosphere, how the magnetic field varies in space and time, in ways that help interpret the Europa magnetic measurements that are central to characterizing the ocean. Simultaneous observations of Europa from two different viewing geometries can constrain three-dimensional properties of any plume activity or atmospheric phenomena that single spacecraft observations can only measure from one angle. The existence of two major missions to the Jovian system arriving within a year of each other reflects the convergence of scientific and political will around the question of ocean world habitability. Both missions passed their critical funding reviews, survived their development phases, launched successfully, and are now on trajectories that will make the 2030s the decade when the question of whether Europa's ocean is habitable will be answered with a degree of rigor that current science can only approximate. The obsession of space agencies with Europa is not merely rhetoric. It is manifest in the most expensive and most technically capable spacecraft ever built for planetary science, traveling to the outer solar system to examine the most compelling potential harbour of life yet identified. The radiation problem is worse than almost any environment humans have ever tried to build for. Jupiter is the largest planet in the solar system, and its size has consequences that extend far beyond its gravitational dominance. Jupiter's magnetic field, generated by the rapid rotation of its metallic hydrogen interior, is the most powerful planetary magnetic field in the solar system, roughly 20,000 times stronger than Earth's. This field creates a magnetosphere that extends millions of kilometers in every direction from the planet. And within that magnetosphere, Jupiter's rapid 10-hour rotation continuously accelerates charged particles, electrons, protons, and heavier ions, to energies far exceeding anything produced by Earth's magnetosphere. The result is a radiation environment that makes Earth's Van Allen belt seem trivial by comparison, and that presents one of the most severe engineering challenges in the history of spacecraft design. Europa orbits Jupiter at a distance of 671,000 kilometers, deep within the most intense portion of the Jovian radiation belts. The radiation flux at Europa's surface is approximately 500,000 rads per day, a unit of absorbed radiation dose. For context, a single rad is enough to cause nausea in a human being. A lethal dose for a human is roughly 400 rads delivered in a short period. Europa's surface receives roughly 540,000 rads of radiation every single day. An unprotected human standing on Europa's surface would receive a lethal dose in about the time it takes to read this sentence. The radiation is not merely dangerous, it is incomprehensible on any scale relevant to biological systems, including the biological systems that build and program spacecraft. The threat to spacecraft electronics is different in character from the threat to biological systems, but equally severe. High-energy electrons, which make up the dominant component of the Jovian radiation belts at Europa's orbital distance, penetrate spacecraft shielding and deposit energy in semiconductor devices, causing two categories of damage. The first is called total ionizing dose damage, the cumulative effect of radiation on the crystalline structure of semiconductor materials, causing transistors and memory cells to malfunction or fail permanently after absorbing a sufficient total dose. The second is called single event effects. Individual high-energy particles passing through a semiconductor device can cause a bit flip, a change in a single stored binary digit, or in severe cases can latch up a device in a permanent fault condition that requires power cycling to clear. In a spacecraft operating autonomously in the outer solar system with a communication delay of up to 45 minutes each way, a single event latch-up that the spacecraft cannot autonomously detect and correct could be fatal. The total ionizing dose that Europa Clipper will accumulate over its 4-year operational period in the Jovian system, despite orbiting Jupiter rather than Europa itself, is estimated at approximately 2.9 million rads. This is the design requirement that every electronic component on the spacecraft must survive while continuing to function correctly. Meeting this requirement required a comprehensive approach to radiation hardening that affected essentially every aspect of the spacecraft's design, from the selection of individual transistors at the level of semiconductor physics, to the shielding architecture at the level of mechanical engineering, to the flight software at the level of computer science. The spacecraft's electronics vault, the central housing for the most sensitive electronics, is constructed from aluminum and tantalum shielding specifically designed to attenuate the high-energy electron flux. Tantalum is particularly effective at stopping electrons because of its high atomic number and density. It converts the kinetic energy of incoming electrons into X-rays before they can reach the sensitive electronics inside. The vault weighs roughly 150 kilograms, a substantial mass allocation in a spacecraft where every kilogram costs significant launch energy. But it provides roughly a factor of 8 reduction in radiation dose inside compared to outside, bringing the interior dose into the range that carefully selected commercial and radiation-hardened electronics can survive. Component selection was itself a major engineering challenge. Radiation-hardened electronic components, transistors, memory chips, processors, designed to survive high radiation doses are available commercially, but they are typically older in design than the most current commercial components, slower, lower in memory capacity, and significantly more expensive. The Europa Clipper's onboard computer, which must execute all the autonomous operations of a complex spacecraft in a high radiation environment over multiple years, is based on radiation-hardened processor technology that is generations behind the processors in consumer electronics, but has been exhaustively tested to survive the Jovian radiation environment. The tension between radiation hardness and computational capability shaped every software design decision on the mission. The radiation challenge is not confined to the spacecraft's electronics. The science instruments themselves must survive radiation exposure while continuing to make precise measurements. The Reason radar, whose antenna elements extend 17 meters on each side of the spacecraft, must maintain calibrated performance despite continuous radiation bombardment. The MASSPEC's mass spectrometer, whose sensitivity depends on the precise geometry of ion paths through electromagnetic fields, must maintain this precision as radiation gradually alters the properties of the materials and electronics that define those fields. Each instrument team developed specific radiation mitigation strategies for their hardware, including redundant circuits, error correction codes, periodic recalibration procedures, and in some cases sacrificial shielding layers designed to absorb radiation dose that would otherwise reach more critical components. The flyby architecture that protects the spacecraft by spending most of its time in lower radiation regions between Europa encounters comes with operational costs. During each flyby, when the spacecraft is closest to Europa and accumulating radiation dose at the highest rate, it must simultaneously operate all 9 instruments, maintain communication with Earth, navigate precisely, and manage its power and thermal systems. The flyby durations, typically a few hours from first close approach to final departure, demand that every observation be scheduled with extreme precision, and that the spacecraft's autonomous systems handle any anomalies without intervention from Earth, since a communication delay of up to 45 minutes makes real-time ground commanding impossible during time-critical close approaches. The radiation environment also affects the scientific measurements themselves in ways that must be carefully accounted for. High-energy electrons striking detector surfaces can produce signals indistinguishable from real photons or particles, creating false counts in instruments sensitive to light or charge particles. The magnetometer measurements must be corrected for the spacecraft charging effects caused by radiation interaction with the spacecraft structure. The plasma wave instruments must distinguish the electromagnetic emissions from the Jovian radiation belts themselves from the signals produced by Europa's space environment. Doing this science in the most intense natural radiation environment in the solar system, with instruments that must survive years of exposure, is an engineering and scientific achievement with no precedent in the history of space exploration. Landing on Europa may be the most difficult thing humanity has ever attempted. The Europa Clipper will answer the question of whether Europa's ocean is habitable. It will not answer the question of whether the ocean is inhabited. That deeper question, the one that motivates the obsession more than any other, requires detecting biosignatures in material from the ocean, either through the analysis of plume material sampled during flybys, or ultimately through direct access to the ocean or its immediate vicinity. Plume sampling, if the plumes are real and the Clipper encounters them, might provide tantalizing evidence. But definitive detection of life, the kind of detection that would withstand the scrutiny of the scientific community and the skepticism of a civilization confronting the most consequential discovery in human history, almost certainly requires landing on Europa's surface and either analysing material directly or preparing the way for a drilling mission to access the ocean directly. Landing on Europa is not like landing on Mars or the Moon, or any other body that has previously received a lander mission. Every aspect of the landing problem at Europa is more difficult than its analogue elsewhere, and the combination of challenges produces a mission concept whose technical demands approach the boundaries of what current technology can achieve. The radiation problem, already severe for an orbiting spacecraft, is acute for a lander that must survive on Europa's surface for long enough to conduct meaningful science. The surface dose rate of roughly 540,000 rads per day means that a lander operating on Europa's surface for 30 days would accumulate approximately 16 million rads of radiation dose, more than 5 times the total dose the entire Europa Clipper spacecraft is designed to survive over 4 years. Protecting a surface lander's electronics from this radiation dose while keeping the spacecraft light enough to land and operate would require shielding mass that is currently on the edge of what mission mass budgets could accommodate with existing launch vehicles. The surface environment adds further complications. Europa's surface temperature, roughly negative 170 degrees Celsius, is cold enough that most conventional spacecraft materials become brittle and lose their design mechanical properties. Propellant systems must function at these extreme temperatures, requiring either heated propellant tanks, which consume power continuously, or propellant formulations specifically selected for low temperature performance. The surface ice, while appearing solid in remote observations, has unknown mechanical properties at the scale of a landing spacecraft. It could be fine-grained and soft, creating a landing hazard analogous to landing in deep powder snow. It could be fractured and uneven, creating stability challenges for a lander attempting to maintain an upright position for weeks or months. It could contain pockets of relatively warmer, ductile ice near the surface in geologically active regions, creating the risk of a lander slowly sinking into the surface. Navigation to a precise surface landing is more demanding at Europa than at Mars or the Moon, because Jupiter's powerful gravitational field and the complex orbital dynamics of the Galilean Moon system make trajectory prediction and spacecraft navigation more computationally intensive and more sensitive to small errors. Europa's gravity, Roughly 13% of Earth's surface gravity means a lander descending under thrust control must manage its fuel consumption carefully to avoid running out of propellant before touchdown, particularly if landing in a geologically interesting region requires a precision landing near specific geological features that may be small in extent. The science return from a Europa lander is the prize that makes all these engineering difficulties worth pursuing. A lander sitting on Europa's surface could perform measurements that no flyby spacecraft can replicate. It could directly sample the surface ice and non-ice materials, measuring their chemical composition with instruments far more sensitive than anything that could fit on a flyby spacecraft. It could drill shallow holes into the ice to access material below the radiation process surface layer, reaching ice that has been in contact with the ocean relatively recently, and may preserve organic chemistry that the harsh surface radiation would destroy if exposed to space. It could monitor seismic activity, measuring the vibrations propagating through Europa's ice shell from the tidal flexing hydrothermal activity or mechanical movement at the ocean ice boundary. A seismic record that would constrain the ice shell's internal structure far more precisely than any remote measurement. NASA's pre-Clipper concept studies for a Europa lander mission concluded that the most scientifically valuable landing site would be a geologically young chaos region or active ridge system, precisely the locations where the ocean surface chemical exchange is most active and where the surface materials are most likely to contain detectable traces of ocean chemistry. The irony is that these are also the most geologically dynamic regions of Europa's surface, making them the most challenging landing sites from a safety and stability perspective. The safest landing sites, ancient, stable, heavily cratered regions where the surface has been geologically quiet for long periods, are also the scientifically least interesting, containing the most radiation processed and least representative surface material. A lander mission to Europa has not yet been formally approved and funded. The Europa Clipper must first complete its orbital reconnaissance, identifying the most promising landing sites and characterizing the surface conditions sufficiently to design a lander that can operate safely and productively. The Clipper mission is therefore the prerequisite for the lander mission, not merely a scientific precursor, but the source of the engineering data, surface roughness maps, ice shell thickness estimates, geological activity assessments that a lander mission design requires. The path to landing on Europa runs through the Clipper, and the Clipper is now on its way. Drilling through the ice is not science fiction anymore. The ultimate goal of Europa exploration, direct access to the ocean that may harbour life, requires penetrating the ice shell and reaching the liquid water below. In the most optimistic ice shell thickness scenarios, this means drilling through 15 to 25 kilometres of ice. In more pessimistic scenarios, it means drilling through 30 to 50 kilometres. Either way, the engineering challenge is unlike anything previously attempted in the history of technology, and until recently it would have been reasonable to describe direct ocean access as an aspiration so far beyond current capability as to be irrelevant to near-term mission planning. That description is no longer accurate. The past decade has seen rapid development of ice-penetrating technologies, motivated partly by the Europa science case and partly by terrestrial applications, specifically the exploration of subglacial lakes in Antarctica, where liquid water lakes exist beneath several kilometres of polar ice and contain microbial communities that have been isolated from the surface environment for millions of years. The technologies developed to access Antarctic subglacial lakes without contaminating them are directly relevant to the Europa drilling problem, and the lessons learned from Antarctic exploration have significantly advanced the state-of-the-art in ice penetration. The most mature ice-penetrating technology for planetary applications is the thermal drill, a device that melts its way through ice by applying heat to the ice at the drill tip, generating a column of meltwater that refreezes behind the drill as it descends. Thermal drills have significant advantages over conventional mechanical drills for ice penetration. They have no rotating parts subject to mechanical failure. They generate no ice chips that must be removed from the borehole, and they are inherently gentle on any biological or chemical material in the ice, because they do not generate the high temperatures and pressures that mechanical drilling produces. Their disadvantage is power consumption. Melting ice requires significant thermal energy, and in a spacecraft operating on nuclear power at Europa's distance from the Sun, available power is limited. Several research groups have developed and tested thermal drill concepts specifically for the Europa application. NASA's Jet Propulsion Laboratory has been developing a concept called the cryobot, a torpedo-shaped thermal drill designed to melt its way through kilometres of ice on a power budget achievable with a radioisotope power source for over a decade. The most recent versions of the cryobot concept incorporate instruments for measuring the properties of the meltwater as the drill descends, sample collection capabilities for preserving material for analysis at different depths in the ice, and communication systems for transmitting data back through the borehole to a surface relay station and then to an orbiting spacecraft. The Antarctic Analog Program has demonstrated that thermal drilling through kilometres of ice is achievable with current technology, though the scale of the Antarctic demonstrations, the deepest successful penetrations have reached roughly 3 to 4 kilometres into polar ice, is far short of the 15 to 25 kilometres required at Europa. The primary technical gaps between current Antarctic capability and Europa application are power availability, miniaturization of the drill system to fit within a planetary spacecraft, sterilization of the drill to prevent biological contamination of any ocean it accesses, and communication of data from the drill through a long, potentially refrozen borehole. The contamination problem deserves special attention because it has implications beyond engineering. If a Europa drill reaches the ocean and introduces terrestrial microorganisms, bacteria or spores on the drill surface that survive the sterilization process, dormant inside the drill, and revive on contact with the liquid ocean, the contamination could produce a false positive in any subsequent life detection measurement. Worse, if the contamination is sufficiently robust, it could spread through the ocean and permanently alter the biological record of what was there before human arrival. The planetary protection requirements for a mission accessing Europa's ocean are therefore the most stringent in the history of space exploration, requiring sterilization protocols that reduce the probability of viable organism delivery to the ocean to below 1 in 10,000 missions. Meeting planetary protection requirements for an ocean access mission while maintaining a drill system capable of functioning after the sterilization process, since many conventional sterilization methods damage sensitive electronics and mechanisms, is one of the central engineering challenges of the Europa drilling concept. Current research into heat sterilization, radiation sterilization, and ultra-clean assembly procedures is advancing toward the goal of demonstrating a sterilized drill system. But the challenge has not yet been fully solved at the scale required for a planetary mission. The timeline for a Europa drilling mission, given the prerequisite of Clipper science to select the landing site, the development time for a lander mission to precede the drilling mission, and the development time for the drilling technology itself, extends into the 2050s or beyond under current planning assumptions. But the direction is clear, and the technical obstacles, while formidable, are not fundamental physics problems. They are engineering problems with defined research paths and plausible solutions. Drilling through Europa's ice shell is not science fiction. It is a long-term engineering project that is currently in its early development phase. The chemistry of Europa's ocean may already be telling us the answer. One of the most significant developments in Europa science in the years immediately preceding the Europa Clipper's launch came not from spacecraft data, but from Earth-based laboratory experiments and theoretical geochemistry. The question of whether Europa's ocean is habitable rests not only on the presence of liquid water and energy, both well supported, but on the presence of the specific chemical elements and compounds that life requires to build its molecular machinery. The dominant chemical elements in terrestrial biology are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, abbreviated CHNOPS. And understanding whether Europa's ocean contains these elements in forms accessible for biochemistry is critical for assessing its habitability beyond the liquid water criterion. Hydrogen and oxygen are guaranteed since the ocean is water. Sulfur is delivered by Io via the Jovian magnetosphere, as discussed in an earlier chapter. Carbon is present in the outer solar system in abundance, delivered to Europa's surface throughout its history by the cometary and asteroid bombardment that continues at a reduced rate today. Nitrogen is similarly available from the same sources. The element about which the most uncertainty exists and which has attracted the most recent scientific attention is phosphorus. Phosphorus is an essential element for life because it forms the backbone of DNA and RNA, the information-carrying molecules of all known life, and because it is the central element in ATP, adenosine triphosphate, the universal energy currency molecule used by every living cell to store and transfer chemical energy. In Earth's ocean, phosphorus is the primary limiting nutrient in many environments, the element whose scarcity most constrains biological productivity. If Europa's ocean is phosphorus poor, the total biomass it could support, even if life exists, might be severely limited. A 2023 study published in the journal Nature Astronomy used geochemical modelling to investigate the phosphorus content of Europa's ocean. The study modelled the dissolution of phosphorus-bearing minerals from the rocky seafloor into the ocean water, taking into account the temperature, pressure, and pH conditions expected at Europa's ocean floor and the specific mineral compositions expected for a rocky interior of the composition inferred for Europa from its bulk density and solar system formation models. The results were unexpectedly encouraging. The model predicted that Europa's ocean could contain phosphorus concentrations comparable to or potentially exceeding those in Earth's most phosphorus-rich ocean environments. Concentrations sufficient to support substantial biological productivity if the other requirements for life are met. The physical reason for the potentially high phosphorus concentrations is related to the chemistry of ocean floor dissolution at the temperature and pressure conditions expected at Europa's seafloor. On Earth, phosphorus in ocean floor rocks dissolves slowly and is frequently reprecipitated into secondary minerals before it can accumulate in the ocean at high concentrations. At the lower temperatures and higher pressures expected at Europa's seafloor, the dissolution chemistry is different in ways that may inhibit the secondary precipitation that limits phosphorus accumulation in Earth's deep ocean. The result is that a larger fraction of the phosphorus released from seafloor rock weathering may remain dissolved in Europa's ocean, rather than being removed by secondary mineral formation. This theoretical result was not directly confirmable with existing observational data. No spacecraft has yet sampled Europa's ocean or measured its phosphorus content directly, but it substantially strengthened the biochemical habitability case for Europa by addressing the specific element whose availability had been most uncertain. Combined with the evidence for carbon, nitrogen, and sulfur availability, the phosphorus prediction pointed toward an ocean whose chemical composition contains all the elements necessary for biochemistry in potentially sufficient concentrations. The organic chemistry of Europa's surface provides additional observational evidence for the presence of carbon-containing compounds in the system. Webb Space Telescope observations of Europa's surface, released in 2023, detected carbon dioxide ice in specific surface regions, chaos terrain and other geologically disturbed areas, with a distribution consistent with delivery from the subsurface rather than from external sources. Carbon dioxide dissolves readily in water and is produced in biological systems as a metabolic byproduct, but it is also produced by purely abiotic geochemical reactions, so the detection by itself is not evidence for life. Its concentration in regions of enhanced ocean surface exchange, however, is consistent with the carbon dioxide having originated in the ocean and been transported to the surface through the geological processes that create chaos terrain. The Webb observations also detected a compound tentatively identified as a carbon-bearing salt, possibly sodium bicarbonate or sodium carbonate, in the same surface regions where carbon dioxide was concentrated. If confirmed, this detection would indicate that carbon-bearing compounds are actively cycling between the ocean and the surface, and that the ocean's carbon chemistry is sufficiently complex to produce a variety of carbon-containing compounds rather than just simple dissolved carbon dioxide. Carbon chemistry is the foundation of organic chemistry, and the presence of complex carbon cycling in Europa's ocean surface system is a positive indicator for the biochemical richness of the ocean environment. The hydrogen production from serpentinization, the reaction of water with iron and magnesium silicate minerals at the seafloor, provides the most direct energy source for potential chemosynthetic life. Recent thermodynamic calculations of the serpentinization rate at Europa's seafloor, incorporating updated estimates of the seafloor temperature and pressure and the mineral composition of the rocky interior, suggest hydrogen production rates sufficient to support a significant biomass of hydrogen-consuming microorganisms, if they exist. The energy available from hydrogen oxidation at the rates that serpentinization could provide, using either the sulfate or carbon dioxide from the overlying ocean water as the electron acceptor, could in principle support a biosphere of very roughly comparable scale to the chemosynthetic communities at Earth's deep-sea hydrothermal vents, adjusted for the area of Europa's seafloor available for venting. None of these calculations prove that life exists in Europa's ocean. Geochemistry can establish that an environment is habitable, that the energy sources, the chemical elements, and the physical conditions are compatible with life. But it cannot demonstrate that life has actually arisen. The question of life's origin remains poorly understood even for Earth, where we know it occurred, and the conditions required for abiogenesis remain debated. But the convergence of multiple lines of geochemical evidence, liquid water, energy from hydrothermal venting, and tidal heating, the full CHNOPS element inventory in apparently accessible forms, oxidant delivery from the surface, and complex carbon cycling builds a habitability case for Europa that is more comprehensive and more chemically detailed than for any other extraterrestrial environment currently known. What a positive detection of life on Europa would actually mean. The detection of life on Europa would be the most consequential scientific discovery in human history. This is not hyperbole. It is the considered assessment of scientists, philosophers, and scholars across multiple disciplines who have thought carefully about what the discovery would imply. Understanding why requires thinking about what the discovery would actually establish, not just what it would suggest. If life were detected in Europa's ocean, even simple microbial life, even a single unambiguous biosignature in a plume sample, it would establish that life has originated independently at least twice in a single solar system. This is the critical logical step that elevates the discovery from remarkable to civilization-altering. We already know life exists in the universe. We are it. A single example of life proves that life can exist, but tells us nothing about how common life is. Is Earth a miraculous exception, the product of a vanishingly improbable sequence of events that occurred once in the observable universe's history? Or is life a robust, near-inevitable product of chemistry that arises wherever the right conditions exist? A single data point cannot distinguish these possibilities. Two independent origins of life in the same solar system would answer the question conclusively. If life arose independently on both Earth and Europa, two worlds with very different environments, different geological histories, and different energy sources, then life is not a miracle confined to one privileged world. Life is something that chemistry does routinely when given appropriate conditions. A universe with two independent origins of life in one solar system is a universe teeming with life. The statistical inference from 2 points to the whole of a universe containing hundreds of billions of galaxies, each containing hundreds of billions of stars, each potentially hosting ocean worlds, is that life is not rare, but ubiquitous. The word independently deserves emphasis. For a Europa life detection to carry the full weight of this logical implication, the life found on Europa must be demonstrably independent of terrestrial life, not a contamination artifact, and not life that crossed from Earth to Europa, or vice versa, through the meteorite exchange that occasionally transfers material between planets and moons in the inner solar system. The evidence for independent origin would be established through biochemistry. If Europa's life uses the same biochemical machinery as Earth life, the same genetic code, the same amino acids, the same membrane lipids, it might be related to Earth life by ancient transfer rather than independent origin, though this scenario is considered unlikely given Europa's distance and the harshness of interplanetary transfer. If Europa's life uses different biochemical solutions to the same problems, different amino acids, a different genetic code, a different energy currency molecule, it would almost certainly represent an independent origin of life, establishing that life is not a unique accident, but a general phenomenon. The philosophical and cultural reverberations of such a discovery would extend far beyond science. Every major human religion has a cosmological account of creation and humanity's place in it. These accounts vary in their specific claims, but most were formulated in eras when the universe was understood to contain only one world capable of supporting life. The discovery that life exists independently on Europa would require reconsidering these accounts in ways that different traditions would handle differently. Some finding the discovery compatible with existing theology, others finding it profoundly challenging. The cultural adjustment would take generations and would reshape human self-understanding in ways that are difficult to fully anticipate. The practical implications for space exploration would also be transformative. A confirmed detection of life on Europa would establish that ocean worlds are habitable environments and would immediately motivate missions to every other ocean world in the solar system. Enceladus, Titan, Ganymede, Callisto, and any other body confirmed or suspected to harbour liquid water. It would reshape the search for life around other stars, shifting attention from terrestrial planets in stellar habitable zones to the icy moons and subsurface oceans of planets across the galaxy. The astrobiology research program would shift from theoretical speculation about life's prevalence to systematic characterization of the biochemistry, ecology, and evolutionary history of multiple independent biospheres. The specific nature of any detected Europa life would carry its own scientific significance beyond the fact of its existence. If Europa's life is microbial, as is overwhelmingly expected for a world whose complex chemistry has been operating for billions of years, without the photosynthetic oxygen production that made complex multicellular life possible on Earth, its biochemistry would be the most informative data point ever obtained about the diversity of possible biochemistries. Whether it uses carbon-based polymers for information storage, whether it uses proton gradients for energy storage, whether it uses metal cofactors in its enzymes analogous to those in terrestrial enzymes, or whether it has found chemically distinct but functionally analogous solutions to these universal biological problems, would illuminate which aspects of biochemistry are genuinely universal and which are contingent on the specific chemical environment in which life arose. The discovery would demand humility. We would suddenly know that the universe contains at least two independent experiments in life, and we would be forced to acknowledge that we understand almost nothing about the full range of what life can be. Every theory of life's origin, every model of biochemical evolution, every assumption about the prerequisites for complexity and consciousness, all of it would need to be reconsidered in the light of a second independent data point. Science would be richer, more uncertain, and more exciting than at any previous moment in its history. What a negative result would tell us that is almost as important. A genuine negative result from Europa exploration, a comprehensive search that finds no evidence of life in an ocean that is genuinely well characterized as habitable, would be scientifically significant in a way that is harder to communicate, but equally important to a positive detection. Negative results are undervalued in science and in public discourse because they do not provide the satisfying resolution that positive discoveries do. But a carefully obtained, well-characterized negative result from Europa would be one of the most constraining pieces of evidence in the history of astrobiology. The value of a negative result depends entirely on the thoroughness of the search. A negative result that merely reflects the limitations of the instruments used. A failure to detect life not because life is absent, but because the search was not sensitive enough, carries no informational weight. The history of life detection in difficult environments is full of examples where absence of evidence was an artifact of method rather than a real biological absence. For a Europa negative result to be scientifically meaningful, it would need to come from a sufficiently sensitive and comprehensive search that the probability of missing life, if it were present at the level that the habitable ocean should in principle support, was demonstrably low. Achieving this standard for Europa is itself an active area of research. The sensitivity of current biosignature detection methods, the ability to detect specific organic molecules, cellular structures, or metabolic products in a sample varies enormously depending on what kind of life is being searched for. Methods calibrated against terrestrial biochemistry might completely miss life that uses a different biochemical architecture. Distinguishing genuine biosignatures from abiotic chemistry that mimics biological signatures is one of the hardest problems in astrobiology, and there is no universally agreed standard for what constitutes a definitive biosignature. Despite these caveats, a negative result from a comprehensive Europa exploration program combining plume sampling by the Clipper, surface material analysis by a lander, and eventually direct ocean sampling would have profound implications if the search had been sensitive and comprehensive enough. It would establish that a habitable ocean with liquid water, appropriate chemistry, energy sources, and billions of years of geological time does not necessarily produce life. This would be a major constraint on theories of abiogenesis, the process by which life originates from non-living chemistry. The origin of life is currently poorly understood. The conditions necessary and sufficient for abiogenesis are debated, and there is no consensus on how probable the event was on Earth or whether it is likely to occur given only that an environment is habitable. Proposed origins of life span a wide range of assessed probability, from theorists who believe abiogenesis is essentially inevitable in any sufficiently complex chemical system given enough time, to those who believe it requires an extraordinarily specific and improbable sequence of events that occurred on Earth by remarkable chance. These theoretical assessments are currently unconstrained by data because we have only one data point, Earth, and cannot determine from a single example whether the probability of abiogenesis is high or low. A negative result from Europa, carefully obtained, would shift this probability estimate downward. It would suggest that abiogenesis does not occur in every habitable environment, that some additional requirement beyond habitability is necessary, or that the timescale required for abiogenesis is long enough that not every habitable environment has yet produced life in the 4.5 billion years of the solar system's history. Each of these implications would reshape theoretical models of life's origin in specific, productive ways. A negative result would also sharpen the search for what makes Earth special. If Europa's ocean, which appears to satisfy the basic chemical requirements for life, is nonetheless abiotic, then there is something about Earth's environment, history or chemistry that was necessary for the specific event of abiogenesis, and that Europa lacks. Identifying this missing ingredient would be among the most important problems in science, and a confirmed abiotic Europa ocean would provide the comparative data point needed to identify it. The difference between Earth and Europa in the specific chemical details of their water chemistry, their seafloor geology, their delivery of organic material, their tidal dynamics, would become the target of intensive investigation aimed at isolating the factors that distinguish an inhabited from an uninhabited habitable world. Perhaps most importantly, a negative result from Europa would not close the search for life in the outer solar system. Even if Europa's ocean proved abiotic after comprehensive investigation, Enceladus, with its actively venting plumes and confirmed hydrothermal activity, would remain to be explored. Titan, with its complex organic chemistry and potential subsurface water ocean, would remain unexplored at the level needed to address habitability. Ganymede, Callisto, and the ocean worlds of the outer solar system beyond Jupiter would all remain as potential sites of independent abiogenesis. A negative result from Europa would be an important constraint, not a final answer. The political and funding story behind why these missions almost did not happen. The scientific case for exploring Europa has been compelling since the Galileo mission confirmed the subsurface ocean in the late 1990s. The translation of a compelling scientific case into an approved, funded, launched spacecraft took 25 years. A journey through the NASA budget process, the National Academy of Sciences decadal survey process, congressional appropriations, and shifting administrative priorities that at several points came very close to ending the Europa Clipper mission before it existed. Understanding this history is important not just as institutional biography, but because the near-death experiences of the Clipper reveal the structural difficulties of funding long-term, large-scale science that does not produce immediate practical returns. The scientific community's formal advocacy for a Europa mission began in earnest in the early 2000s, following the Galileo mission's confirmation of the subsurface ocean. The 2003 National Academy of Sciences Decadal Survey for Planetary Science, the 10-year priority-setting exercise that the scientific community conducts to guide NASA's planetary program, identified a Europa orbiter as one of the highest science priorities for the coming decade. This was the beginning of a funding saga that would consume more than 2 decades before producing a launched spacecraft. The fundamental problem was cost. Europa's radiation environment requires radiation-hardened electronics, heavy shielding, and specialized design approaches that make a Europa mission far more expensive than comparably ambitious missions to less hostile destinations. Early design concepts for a Europa orbiter, a spacecraft that would orbit Europa directly rather than using the flyby architecture eventually adopted for the Clipper, came in with cost estimates exceeding $4 billion, at a time when NASA's flagship planetary science budget was already heavily committed to other large missions, and when Congress was not inclined to approve a new multi-billion-dollar planetary mission. The 2011 Decadal Survey reaffirmed Europa as a top priority, but explicitly noted that the cost needed to be reduced before the mission could be viable. This triggered years of mission design studies aimed at reducing the cost while preserving the science. The flyby architecture, orbiting Jupiter rather than Europa, making repeated close approaches, emerged from these studies as the approach that could achieve most of the science at significantly lower cost than an orbiter, because it avoided the heavy radiation shielding that a Europa orbiter would require to survive months of continuous radiation exposure in Europa's orbit. Even with the cost-reducing architecture, the mission's budget remained in the $2 to $3 billion range, high enough to be vulnerable in any year when NASA's budget came under pressure. Between 2013 and 2015, the mission went through annual funding battles in which the Obama administration's budget request zeroed out Europa mission funding multiple times, only to have Congress restore the funding each time. The congressional restorations were driven in large part by the advocacy of Representative John Culberson of Texas, whose district included the Johnson Space Center, and who became a powerful champion for the Europa mission, repeatedly inserting language into appropriations bills directing NASA to pursue the mission and providing budget lines that the administration had not requested. The political dynamics of the Europa mission's survival illustrate a broader truth about how large science missions get funded. They require not just scientific merit, but political champions, specific elected officials or administrators who understand the mission's significance and are willing to fight for its funding through budget cycles that otherwise prioritize near-term practical returns. Without Culberson's sustained advocacy during the critical 2013 to 2017 period, it is not clear that the Europa Clipper would have survived the annual budget process and reached the launch pad. The mission scope also went through significant changes driven by cost and technical factors. Early concepts included a Europa lander as part of the same mission as the orbiter, bundling the surface science with the remote sensing in a single spacecraft. The combination was scientifically appealing, but drove cost to levels that made approval essentially impossible. The decision to defer the lander to a future mission and focus the Clipper entirely on the flyby reconnaissance was a pragmatic choice that made the mission financially viable at the cost of deferring the most scientifically ambitious objectives, direct surface access and ocean chemistry measurement, to a mission that has not yet been approved. The total cost of the Europa Clipper mission at launch was approximately $5 billion, including the spacecraft, instruments, launch vehicle, and projected operations through the end of the primary mission. This makes it one of the most expensive planetary science missions in history, and the long development timeline, from the first formal mission proposals in the early 2000s to the October 2024 launch, means that scientists who began working on the mission as junior researchers have spent entire careers getting it off the ground. The patience, persistence, and institutional stamina required to sustain a scientific mission through a quarter-century of budget battles, design revisions, and shifting political winds is itself a remarkable achievement, rarely recognized in the public accounts that focus on the launch and the destination, rather than the decades of work that made both possible. Europa in the context of the other ocean worlds. Enceladus, Titan, Ganymede. Europa is not the only ocean world in the solar system, and the obsession of space agencies with ocean worlds extends beyond Europa to a family of bodies that collectively represent the most significant expansion of the potentially habitable volume of the solar system in the history of planetary science. Understanding Europa's place in this family, what makes it unique, what it shares with its cousins, and how the different ocean worlds complement each other as targets for the search for life, provides essential context for why the Europa obsession exists and where it fits in the broader story of astrobiology. Enceladus, Saturn's small moon at roughly 500 kilometers in diameter, is in many respects the most tantalizing single object in astrobiology because it has already provided something that Europa has not yet yielded: directly sampled ocean material. The Cassini spacecraft, operating in the Saturnian system, from 2004 to 2017, flew through Enceladus's geysers more than 20 times and measured their composition in detail. The plume measurements revealed water vapor, ice particles, sodium and potassium salts consistent with water-rock interaction, complex organic molecules including some of the building blocks of amino acids, molecular hydrogen indicating active hydrothermal chemistry, and silica particles consistent with temperatures at the hydrothermal vents exceeding 90 degrees Celsius. Every measurement made the habitability case stronger, and no measurement contradicted the picture of an ocean with active hydrothermal chemistry and the chemical ingredients for life. Enceladus's advantage over Europa is the accessibility of its ocean material. The plumes deliver ocean samples directly to passing spacecraft. Its disadvantage relative to Europa is its small size. With less mass and less tidal heating than Europa, its ocean may be smaller and its geological activity less sustained over the long term, potentially limiting the total time available for abiogenesis to occur. The liquid water ocean in Enceladus may also be geologically younger than Europa's, since the tidal heating that maintains it is sensitive to orbital resonance conditions that could have changed over the Moon's history. A younger ocean has had less time for life to originate if it requires a minimum timescale of chemical evolution. Titan, Saturn's largest moon at roughly 5,150 kilometers in diameter, occupies a completely different position in the ocean world family. It may harbour a subsurface liquid water ocean similar to Europa's and Enceladus's, but its most distinctive feature is its surface environment: a thick nitrogen atmosphere, active weather systems involving liquid methane rather than water, rivers and lakes of liquid methane on the surface, and the most complex organic chemistry of any body in the solar system other than Earth. Titan's surface organic chemistry, produced by photochemical reactions in the upper atmosphere, includes tholins, amino acid precursors, and a diversity of complex organic molecules that represent the most Earth-like prebiotic chemistry ever observed in the solar system outside of Earth itself. The astrobiological interest in Titan is therefore dual. The subsurface water ocean, if it exists, and if it contains sufficient energy and chemical inputs, might support water-based life analogous to Europa's potential biosphere. But more speculatively, Titan's surface methane lakes and seas might support a completely different kind of life, chemistry-based life that uses liquid methane rather than liquid water as its solvent. Such life, if it exists, would use completely different biochemistry from anything known on Earth, with different solvents, different reaction mechanisms, and potentially radically different molecular structures for information storage and metabolism. NASA's Dragonfly mission, a rotorcraft lander approved and in development, will land on Titan in the 2030s and conduct detailed surface chemistry measurements relevant to both the organic chemistry question and the habitability assessment. Ganymede, the target of the JUICE mission, is the largest moon in the solar system and the only moon known to have its own magnetic field. Like Europa, it appears to harbour a subsurface ocean between an outer ice shell and a rocky interior, based on magnetic induction measurements from the Galileo spacecraft. The ocean is thought to be deeper within Ganymede's interior than Europa's ocean, located between layers of high-pressure ice rather than in direct contact with the rocky seafloor, which has implications for the water-rock interaction that might support hydrothermal chemistry. A subsurface ocean sandwiched between ice layers rather than between ice and rock might have less geochemical energy input and less chemical exchange with silicate minerals, potentially making Ganymede's ocean less habitable than Europa's, despite being liquid. The comparison between the different ocean worlds illuminates what makes Europa particularly compelling. It has a large ocean in direct contact with a rocky seafloor, providing the most direct analogue to the hydrothermal environments where life on Earth may have originated. it shows abundant evidence for geological activity that cycles material between ocean and surface. It orbits in a powerful radiation environment that, while challenging for spacecraft, produces oxidant chemistry that may enhance the ocean's metabolic potential. And it has been confirmed as having a global ocean by independent lines of evidence from multiple spacecraft over decades. The combination of these factors makes it the most comprehensively characterized and most robustly habitable of the known ocean worlds, which is why it is the primary target of the most capable planetary science mission ever launched. The broader ocean world family also provides the scientific context for understanding what a positive or negative result at Europa would mean. If Europa's ocean, with its apparently favourable habitability characteristics, harbours no life, then the bar for abiogenesis is higher than the basic habitability criteria suggest, and the other ocean worlds with less favourable chemistry or less geochemical energy would be correspondingly less likely to harbour life. If Europa harbours life, then the roughly dozen confirmed or suspected ocean worlds in the solar system, and the presumably far larger number in other stellar systems, become compelling targets for a broad astrobiology program. The timeline from first flyby to first sample, what the next 50 years looks like. The Europa Clipper is currently en route to Jupiter on a trajectory that will bring it to the Jovian system in April 2030. Its arrival will begin the first phase of comprehensive Europa science, the systematic flyby campaign that will produce the most detailed characterization of Europa's ocean, ice shell, surface chemistry, and geological activity ever achieved. Over 4 years of operations, the 49 planned flybys will build up a global picture of Europa at a level of detail that will support every subsequent step in the exploration program. The most immediately consequential early science will come from the Reason ice-penetrating radar and the magnetometer. The radar's measurements of ice shell thickness and internal structure will either confirm the existing ice shell models or reveal surprises that reshape understanding of the ocean ice boundary and the processes controlling material exchange. The magnetometer's improved measurements of the induced magnetic field will tighten constraints on the ocean's electrical conductivity and therefore its salt content, providing the first quantitative picture of the ocean's chemistry from a direct physical measurement. Together, these two instruments will answer the most fundamental outstanding questions about the ocean's basic properties within the first year of operations. The plume search will begin immediately upon arrival. Every flyby will include ultraviolet and mass spectrometer observations searching for water vapour and organic molecules in the space around Europa. If plumes exist at the level of activity suggested by the Hubble detections, the probability of detecting at least one plume encounter over 49 flybys is high, and even a single plume encounter with the MassSpec's mass spectrometer would provide revolutionary data about the ocean's organic chemistry. The detection of complex organic molecules in a confirmed plume would be the most direct evidence yet obtained for the chemical richness of the ocean, and would dramatically accelerate the scientific case for a follow-on lander mission. The Clipper primary mission is planned to run through 2034, though mission extensions are possible if the spacecraft and instruments remain healthy. The data from the primary mission will be analysed by the scientific community for years, and the synthesis of all observations will produce recommendations for the high-priority targets of subsequent missions. Specifically, the sites where a lander should be deployed for detailed surface analysis. The Europa lander mission, if approved by NASA and funded by Congress, would likely launch in the late 2030s or early 2040s, given the development timeline required for a mission of its complexity. This would target arrival at Europa in the early to mid-2040s. A lander successfully deployed in a scientifically productive site, a young chaos region or active ridge system identified by the Clipper, would conduct surface and shallow subsurface chemistry analysis over a surface lifetime of perhaps 30 to 60 days. Limited, by the accumulated radiation dose on the lander's electronics. The science return from even a short surface mission would be transformative. Direct measurement of organic chemistry in surface materials, shallow drilling to access radiation-protected ice, seismic monitoring of ice shell activity. The results from a lander mission would inform the design of the most ambitious and most technically challenging phase of Europa exploration. The deep drilling mission aimed at penetrating the ice shell and accessing the ocean directly. Given the development timeline for the drilling technology, the prerequisite of lander reconnaissance to characterize the surface and identify the best drill site, and the time required for mission approval and development after the lander results are analyzed, a deep drilling mission would likely not launch before the 2050s under optimistic assumptions. The Ocean Access mission represents the final step in the sequence that begins with the Clipper's orbital reconnaissance, a step that, if technically successful, would allow direct measurement of ocean chemistry and would provide the definitive answer to the question of whether Europa's ocean is inhabited. The 50-year arc from the Clipper's arrival at Jupiter in 2030 to the first ocean access in the 2050s or beyond is long by any standard of human patience. But it is not unreasonably long by the standards of exploration programs that address questions of fundamental importance. The Apollo program, from John Kennedy's 1961 commitment to the first lunar landing in 1969, took 8 years. The Human Genome Project took 13 years from formal initiation to completion. The CERN Large Hadron Collider took 25 years from concept to first collisions. Exploration programs of this ambition and importance operate on the timescales they require, not on the timescales that impatient observers might prefer. The answer to the question of whether Europa's ocean harbours life will come within this century. The spacecraft that will begin answering that question is already flying through the solar system on its way to Jupiter. The next 50 years of space exploration will be defined in part by what it finds. Why Europa is the most important destination in the solar system right now. The case for Europa's primacy among planetary science destinations comes down to a single, unambiguous assessment. It is the place in the solar system where the probability of finding life is highest, given current scientific knowledge, and finding life, or establishing with confidence that a comprehensively habitable environment does not harbour life, would provide the most important scientific result, obtainable by any mission currently under development or planned for the foreseeable future. This assessment is not universally shared. Mars receives more total mission investment than Europa, driven partly by its accessibility, partly by the long history of Mars exploration that has built up infrastructure, knowledge, and institutional momentum, and partly by the near-term human exploration agenda that has no near-term analogue for the outer solar system. The argument for Mars as the primary life search destination rests on the evidence for ancient liquid water on Mars's surface, the discovery of subsurface liquid water in some recent radar observations, and the accessibility of Martian surface material through the ongoing sample return program. If life ever existed on Mars during its warmer, wetter ancient period, fossil evidence might be preserved in Martian rocks, and the Mars Sample Return mission, when it eventually retrieves the Perseverance rover's sample cache, might detect it. The comparison between Mars and Europa as life search destinations reflects a fundamental uncertainty about what life requires. A world with a long history of surface liquid water that is now cold and dry, or a world with a persistent subsurface ocean that is cold but continuously liquid. The Mars case depends on finding fossils of ancient life. The Europa case offers the possibility of finding extant living organisms in an ocean that may be active today. For the question of whether life currently exists in the solar system beyond Earth, Europa provides the more direct search target. The significance of Europa extends beyond the specific question of life to the broader question of what the solar system, and by extension, the universe, is like. Before the outer solar system exploration that began with Voyager, the solar system appeared to be a place where liquid water, and therefore life, existed only in the narrow habitable zone around the Sun, on one planet. The discovery of Europa's ocean transformed this picture. The solar system contains more liquid water in the subsurface oceans of its icy moons than on all its rocky planets combined, and this water exists at distances from the Sun, where it was theoretically impossible under the old habitable zone framework. This transformation of the solar system's apparent character is a preview of what the confirmation of ocean world habitability would mean for understanding the universe. The Milky Way galaxy contains hundreds of billions of planetary systems. Many of these systems contain giant planets analogous to Jupiter and Saturn, and those giant planets presumably host icy moons subject to tidal heating analogous to what drives Europa's ocean. The fraction of these moons with subsurface oceans is unknown, but could be substantial. And if even a small fraction of them harbour life, the universe's inhabited volume is vastly larger than any pre-Europa habitable zone calculation would have suggested. Europa also sits at the intersection of the two deepest questions in science. How does life originate, and how common is life in the universe? These questions are connected. The answer to one constrains the answer to the other, and Europa is the place where the answer to both might become accessible for the first time. No other target in solar system exploration currently combines a confirmed habitable environment with the proximity and accessibility needed to conduct a definitive search for life within a mission timeline that current technology can support. The obsession of space agencies with Europa is therefore not merely enthusiasm for a scientifically interesting moon. It is a recognition that Europa represents a threshold, a boundary between a universe where we are alone and a universe where we have company, and the closest accessible point to that boundary currently known. Every spacecraft sent to Europa, every dollar invested in its exploration, every year spent developing the technology to drill through its ice, is an investment in crossing that threshold, in finally answering the question that has haunted human consciousness since people first looked at the night sky and wondered whether the stars contained other worlds and whether those worlds contained other lives. The answer is close. Not certain, not guaranteed, but close in the way that scientific answers become close when the experiments needed to obtain them are underway. The Europa Clipper is flying. The data will come. And when it does, the answer, whether it is yes or no, or something more complicated than either, will be the most important thing science has ever told us. The ice moon that asked the oldest question. The oldest question in human intellectual history is not a philosophical abstraction. It is visceral and immediate. Are we alone? It has been asked implicitly by every civilization that looked up at the sky and wondered what the stars were, and explicitly by every scientist and philosopher who recognized that the universe's scale made the uniqueness of life on Earth seem improbable. For most of human history, the question was unanswerable. The universe was too large, our instruments too limited, and our understanding of what life requires too primitive to meaningfully test whether life existed elsewhere. The question was real, but it could only be felt, not investigated. Europa made the question answerable, not by providing the answer, that work is still underway, but by providing a specific, accessible, physically real target where the answer could in principle be obtained. Before Europa, the search for extraterrestrial life was oriented primarily toward Mars, toward signals from distant civilizations, or toward theoretical speculation about the range of habitable environments in other stellar systems. These were and are legitimate directions, but none of them provided the combination of a confirmed habitable environment and the proximity needed to search it within the lifetime of a single space program. Europa provided both. The ice shell that covers Europa's ocean is not just a geological feature. It is a boundary between what we know and what we might know, between the universe as we have understood it for all of human history, with life existing only on Earth, and the universe as it might be, with life distributed through the ocean worlds of the solar system and the galaxy. Every crack in that ice, every ridge built by tidal flexing, every chaos region where the ocean's influence reaches toward the surface, is a reminder that the answer is down there, beneath kilometres of ice, accessible to the right instruments at the right moment. The people who built the Europa Clipper, who spent careers advocating for it in budget hearings and design reviews and scientific conferences, who solved the radiation shielding problem and the navigation challenge and the instrument sensitivity requirements, were working toward a moment that most of them will not live to see. The moment when a drill penetrates the last metre of ice and a sample of Europa's ocean is analysed for the chemistry of life. But the arc of the work they did bends toward that moment, and the trajectory of the spacecraft they built traces a path toward the answer. The oldest question has a specific address now. Buried beneath the ice of a small moon orbiting Jupiter, 628 million kilometres from the Sun. And we are on our way there.